this lesson is on orbital filling diagrams and electron dot diagrams, which are also known as Lewis structures, and dot notation. Orbital filling diagrams are when you draw the electrons in their orbitals. So, for instance, if the electron configuration had a 1s2 in it, okay, the orbital filling diagram would show one circle because it's in 1s, there's only one orbital in an s sublevel, and the two electrons will be shown by lines in opposite directions. If you had let's say you had a 2p6 in your electron configuration, your orbital diagram would have three circles. The circle doesn't represent a sphere as in an s sublevel. The circle is representing the orbitals. So because p has three orbitals, 2 electrons can fit in each. So if there's 6 total, we would put 6 electrons, 6 lines, 2 in each. Underneath each one, you'd label it. So we'd label the first one 1s. Under the 3, we'd label it 2p. Notice I didn't write the number of electrons like 2p6 because it's shown by the lines. If you had a 3d, let's say there were 10 electrons. D has 5 orbitals, so you draw 3 circles, label it 3d. 10 electrons would be 2 in each. And a 4f, let's say there were 14. For f, you would have 7 orbitals. There's 14, 2 electrons in each. So you would draw all of these for every part of your electron configuration. There are 2 rules to this. The first is called Hund's rule. Hund's rule states that you need to fill each orbital with 1 electron before they double up. With 2 electrons. So for example, if you had 3d7 in your configuration, you would draw D, so you'd draw 5 orbitals. You label it 3d. 7 electrons. You'd put 1 in each first. There's your 5. Now, since there's more than 5, we have to go back and double up. Okay? It's just like students on a school bus. If there were 50 seats and there were 50 students, you would each take your own seat. You wouldn't double up unless you have to. 20 more kids get on the bus, well, now you're going to have to double up seats. The electrons are exactly the same way. The other rule, and I'm just going to put a star there, doesn't have a name, is that you need to draw all of the orbitals even if they are empty. So for example, if you had 2p1, you'd have 3 p orbitals. We'd label it 2p. Only 1 electron would look like that. You still have to draw the other ones to show that those orbitals exist and that they are just empty. Okay? This would be incorrect if you just had that. Okay? There are a couple other ways to write this. Sometimes you will see these written in boxes with up and down arrows. That is the same as the circle with the two lines. Sometimes you'll see these as just a line with the two arrows. Okay? The reason the arrows are opposite and the reason the lines are diagonal, okay, is because the electrons have opposite spins. So they're in the same orbital, but one's spinning one way and the other spinning the other way. For instance, clockwise and counterclockwise. Okay, that is their last quantum number. That's what makes them different. A couple examples. So if we were to do fluorine's electron configuration, okay, fluorine would be 1s2. So I write 1s, I draw my orbital, draw my 2 electrons. Leave a little space, then comes 2s, 2. Leave a little space, after that would be 2p with my 3 orbitals. And it'd be 3p5, so 1, 2, 3, 4, 5. Let's do one more. If we were to do scandium, okay, we'd have 1s, 2, 2s, 2, 2p, 6, then we'd have 3s2, and 3p6, then 4s, 2, and then 3d. You have to draw the 5 orbitals, but it's just 3d1. So that's orbital filling diagrams. The next topic is electron dot diagrams. These are also known as Lewis structures. And dot notation. So one of these would look like this. For example, fluorine would have 7 dots around it. You can see dots are in the top and bottom, left and right, and they are grouped in pairs. The dots represent what we call valence electrons, and the symbol represents everything else. So let's write what valence electrons are and then come back and label our example. Valence electrons are electrons in the outermost shell of an atom. So this would be their highest energy level. So these are furthest away from the nucleus. And what's key about this is going to come into play a lot in other chapters, is that these determine the atom's chemical properties. So if we go back up to our example with fluorine, let's label that the dots represent the valence electrons, and that the symbol represents the nucleus and inner electrons. Fluorine has 7 because we have 1s2, 2s2, 2p5. So our highest energy level, furthest away from the nucleus, would be 2. 2 plus 5 is 7 valence electrons. If we were to do lithium, lithium would be 1s2, 2s1. So highest energy level is 2 with 1 electron. So we would draw the symbol, and we'd have 1 dot. That dot can be on any side, does not matter. What matters is it's on a side, the left, the right, the top, or the bottom. If we were to do boron, 1s2, 2s2, 2p1. Highest energy level is 2, total of 3 electrons, so boron would have 1, 2, 3. Just like in the orbital filling diagrams, the electrons are going to space out. This is where they are in their excited state. This is how they bond, which we'll get to in chapter 6. Doesn't matter which 3 sides, just 3 sides. If we were to do nitrogen, we would have 1s2, 2s2, 2p3. So 2 is the highest energy level. 2 plus 3 is 5. So nitrogen, write the symbol. I like to go 1, 2, 3, 4, so I know I'm hitting each side first, and then I'm going to go back and double them up. Make sure that wherever they are, doesn't matter which side, they look like a pair. What's incorrect would be to write nitrogen and then do 1, 2, 3, 4, 5, something like that. Okay?